to write over here, boiling. Okay, so evaporation, if I think of a container here, let's say this is air above, and let's say this is water. Okay, so that line over there is the surface of the water, or the boundary between the two media, the water and the air above. And let me focus on a collision between two water molecules on the surface of the water. So I'm going to draw a water molecule here. It would be H2O, right? Well, I'll just draw it like this. Like a Mickey Mouse face, H2O. Suppose this water molecule is just hanging out over there. And I'm going to draw another one just so that we can keep track of the collision. And suppose we have from underneath, I'm just exaggerating, the sizes over here. Suppose that underneath is another water molecule that's going this way. And it's moving that way. Okay, they're about to collide. Yes? What if the water molecule that's coming in from below has an energy, I'll say 8. I'm not going to write down the units. I'm not going to say 8 joules. That's a lot of energy for a molecule, but let's just say it's 8. Let me leave out the units. So E stands for energy. And let's say that the energy of this molecule maybe just stops for whatever reason. It just hit another molecule, and let's say it stopped. Just for the sake of argument. Okay? Or you can make it 1 if you like, or whatever, but Now, boom, they collide. And as a result of that collision, this molecule ends up getting expelled from the water. So then it goes here, and now it's moving this way. And let me make the energy of that 2. And the other molecule, the blue one, hit that molecule, kicked it out of the water, and bounced back, right? So it recoiled and sort of went this way. From conservation of energy, what would have to be the energy of this molecule?
6.
It would be going this way, right? At some other speed, right? So, but I'm going to say the energy is 6. Correct. Because the incoming fast molecule had some kinetic energy, boom, it collided with the other one and transferred some energy to the other molecule, making it leave with units, let's say 2 units of energy. But from conservation of energy, before the collision, the energy of both of them was 8 plus 0 is 8. After the collision, 2 plus 6 has to be 8, right? Now, what do you notice here? What you notice here is that the molecule that remains in the liquid has less energy than what it had before when the other one leaves. So as a whole, the liquid is cooled. So evaporation is a cooling process. For the liquid, right? And by the way, in boiling, right, let's say you have air and you have water. This is also a cooling process. I'm going to write down the similarities between them. Another similarity between them is that both of these processes involve a liquid turning into a gas, right? The molecules are getting kicked out of the liquid, so, the liquid turns into a gas. And when you boil water, for example, in liquid, turns into a gas. If it's water, you call it steam, but that's just a name. Liquid turns into a gas. So these are similarities between them, right? Now, what are some of the differences between them? The difference is that evaporation, it's a process that takes place specifically where?
At the surface of the
On
water?
the surface. From the surface is where the molecules or atoms of the liquid leave the liquid, right? So evaporation is a surface effect. On the other hand, when the water boils, the formation of,
Convection.
water vapor, right, is all over the place. It happens there, 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 it happens all over the place. The boiling process happens, the formation of water, bubbles, right, of water vapor in there. It happens all over the place. So it is not a surface effect only. It happens throughout the entire liquid, right? So boiling occurs throughout the volume of the liquid. In fact, the surfaces are, it's where a lot of it happens, throughout the volume of the liquid. Not just the surface. That's one difference between these two processes. And there is another difference. Anyone know what that other difference is?
This is driven by heat energy and this is driven by kinetic energy. I guess they're related, but I mean, that's predominantly, by a lot of thermal energy, right?
Mm-hmm. That'll affect at what temperature is going to happen. But the other difference is that boiling, depending on the pressure that the atmosphere exerts, happens at one temperature. And that's it. So for water, and if the pressure is 1 atmosphere, it happens, clean water, at 100 degrees Celsius, period. Not 101 degrees Celsius, not 99 degrees Celsius, 100 degrees Celsius. Evaporation can happen at any temperature. The water can evaporate even if it's at 1 degree Celsius, 2 degrees Celsius. The hotter it is, the closer it is to 100 degrees, the more quickly it'll evaporate, because the molecules are jiggling more vigorously and the collisions will be, more violent, and more of them are going to get kicked out of the liquid. So the other difference is that boiling, right, occurs at one temperature only. And that temperature, depends on the pressure. Evaporation can take place at any temperature of the liquid. So for example, if I take a cup and I put some water in there and I put it over there and I would just leave it there, right? A day or 2 or 3, give it some time, that cup is gonna be empty. Because the water evaporated into the rest of the room. Now, it didn't boil. It's not like, oh, what happened to the cup? Either somebody drank the water, or you might think, oh, it boiled away. But in order for it to boil in this room, right, the temperature of the water would have to be 100 degrees Celsius. No, we're only like at 23 degrees Celsius in this room. We're nowhere near 100 degrees Celsius. So what happens is that because of the collisions of the water molecules on the surface, they get kicked out, they get kicked out, they get kicked out, they get kicked out, and then they're all gone, into here. The water molecules that used to make up the liquid are now part of the air in this room. Then we have water vapor, more water vapor in the room. Yes? By the way, what would happen though if this water molecule over here went like this, boom, and landed? It's gonna bring back the 2 units of energy, right? Just like it never left. That wouldn't be cooling. Once you got the 6 plus the 2, you still have the 8. So evaporation is a cooling process if the molecules don't come back. And one way to ensure that they don't come back, like maybe you bought some hot coffee or hot tea or hot soup and you want to drink it and you don't want to wait that long, you want to help the cooling process, you can just blow over it to ensure that the molecules don't land back into the liquid, that they leave. So blowing over your soup or hot coffee or hot drink will help the evaporation process so that it cools down more quickly, so you drink it sooner rather than later. Another thing you can do here, my grandmother used to do that a lot, but she also used to do something that it didn't seem to make sense. But after studying some physics, it does make some sense. She used to, my maternal grandmother, she used to drink a lot of coffee, and she would pour the coffee on a saucer plate. And you would ask me, what the heck, why? You got the cup over there, why? So it's like she would pour it on a saucer plate. Well, now there's the coffee, right? So what happens?
Is there more surface area?
You got more surface area. So there are more places where the water molecules or the molecules of the hot liquid here will leave, and so it's going to cool down more quickly, so she could drink it faster. Right? So I don't know if you ever had someone you just have increased surface area. So the evaporation process, right? The higher the temperature of the liquid, the more quickly it will evaporate. Number 2, the more surface area there is, the more places where those molecules can undergo those billiard ball physics collisions on the surface. Evaporation is a surface effect. Boiling is a process that occurs throughout the entire. You'll see the bubbles forming all over the place throughout the entire liquid. Evaporation only on the surface. Right? So you take a shower and you dry your skin with a towel. If you grab the towel and you make it into a bowl and you throw it in the corner in the morning before coming to class, you may go there later. Well, not this day because it's very hot, but you may go there later in the day. It might still be wet in some places. But if if you spread it out, then it'll dry more quickly because then you have sort of like increase the surface area from where the molecules can be. So anyway, just wanted to say something about, because, sometimes people use these 2 terms interchangeably, but boiling, and wait a minute, right? Didn't we say that when water boils at 100 degrees Celsius with the pressures of the atmosphere, what happens? What did we say about the temperature? What did we say?
It doesn't change.
It doesn't change. So how could it cool down if it's not changing? We have a little problem now, right? I just said that it's a cooling process, but wait a minute. While the water boils, the temperature stays at 100 degrees Celsius. And this has to do with the comment that Francis made. To make it boil, you put in some fire over here. So you add thermal energy to make it boil. And what happens is that you're adding this energy to the water, and when the boiling process happens, you got the bubbles living over here, and they take away energy, right? So this energy is the one that cools the liquid, but because you're adding it over here, so what happens is that the rate of energy added equals the rate at which the energy leaves, and the temperature stays the same. So you gotta keep adding that energy to keep it boiling, so the temperature stays the same. If you stop this, right, then it would just be evaporating like that. So the reason why the temperature remains the same as it boils is because you have, even though it's like the water is trying to cool down, but you keep heating it up at the bottom by putting the water on the fire or some source of energy. Okay. Anyway. Okay, so just by the way, the reason why we sweat, it's hot outside these days, right? If you go jogging, you're going to be sweating very quickly. Your body temperature goes up, and your body has this way of regulating your temperature by saying, man, you're heating up too much. That's not good. Right? So then you begin to sweat. And the idea is that the sweat evaporates from your skin, therefore cooling you down to lower your temperature. Some people go to the hospital because they get very sick and they have a very, very high temperature, and my goodness, they're trying different things to lower the temperature of this person. Sometimes they even put them in ice cold water, to bring the temperature down. But, maybe before they go to that extreme, they rub alcohol on the skin of the person. And the alcohol evaporates very quickly. And that cools you down. You take a shower, and you're, taking the shower in the shower region, right? You got the water here. There's a lot of water vapor in there because, then you finish taking the shower, and as soon as you step outside the shower region, you feel a little chilly, right? Because now you have evaporation of some of the water from your skin, and that cools you down, right? In the shower region, right, you have evaporation, but you got a lot of water vapor in there that's also condensing on your skin. So if boiling is a cooling process, condensation is a heating process, right? And the days that you feel the worst, is when it's very humid. When it's very humid, it's like, it's like, my goodness, it's like, so your body is trying to cool you down by evaporating, sweat from your skin. But then if it's humid, that means that there's a lot of water vapor in the air that's also condensing on your skin. And so it's like, with that water vapor condensing on your skin, right? It's counteracting the fact that your body is cooling down by evaporation of sweat. So it counteracts, right? And if the rate of condensation of that water vapor on your skin is the same as the rate of that you're attempting to cool by evaporating sweat, it's like you're not really getting cooled down, and well. It doesn't get very humid around here, but it does get humid every now and then, every few weeks in the year or so.
I feel like lately with the heat wave, it's been more humid.
Huh?
I said I feel like lately it's been more humid with the heat wave because it'll only be like 85.
I think there's some storm going on down in Mexico, and
I saw that it like kind of, as soon as it got
Feel it,
closer to
yeah.
San Diego, it kind of curved off a little more.
Mm-hmm. Yeah. But I lived in New York City for a long time, for many years. And I mean, the winters are cold and the summers are hot and humid too. The East Coast is. By the way, maybe I should say something about why Southern California, next to the ocean or near the ocean, is relatively cool. I guess we can say something given what we've discussed. Because If you consider, for example, the same latitude as Southern California, say LA area, Orange County, and you go to the East Coast, the same latitude, you know, that would be like what?
Georgia.
Or thereabouts. It's humid over there. I mean, and I mean, it's hot in the summer, and it's colder than here in the winter time. So why is that? And there are two reasons why that's the case. Can I erase this, please? Can I erase this? Sure.